For decades, the question that mattered in semiconductors was simple. How small can you go? The company that printed the tiniest transistors won. Everyone else fell behind. That rule shaped geopolitics, powered the AI revolution, and made TSMC one of the most important companies on Earth. But what if the race itself just changed? What if the next leap forward has almost nothing to do with making transistors smaller at all? And what if the company that triggered this shift did so not because it had the best equipment, but precisely because it couldn't get it? That's the paradox at the heart of Huawei's recent semiconductor announcement. And it's forcing engineers everywhere to reconsider what advanced actually means. The backstory is well known, but it matters. In 2019 and 2020, the US government imposed sweeping restrictions on Huawei's access to foreign chip technology. By 2022, the company was effectively cut off from the most advanced chip-making equipment on the planet. The most critical of those machines is the EUV lithography system, made exclusively by the Dutch company ASML. It costs around $200 million, weighs as much as 2 commercial airplanes, and uses extreme ultraviolet light to print circuit patterns so fine that a single atom of contamination would ruin them. Huawei cannot buy one. Neither can SMIC, the Chinese foundry that manufactures Huawei's chips. SMIC has been doing something genuinely impressive with older DUV machines, using a technique called multi-patterning to push toward what is roughly considered a 7-nanometer equivalent process. But every extra step adds cost, complexity, and defect risk. And here's a ceiling. By late 2024, reports suggested SMIC's 7-nanometer yields were struggling, with some estimates as low as 20%. Huawei knew this. The traditional scaling path was closing, so their engineers started asking a different question. What if the way we've been measuring progress is incomplete? Here's something that surprises most people. Modern computers are not mostly limited by how fast their transistors can switch. They're increasingly limited by how long it takes information to travel from one part of the chip to another. Think about that. The processing part is no longer the bottleneck. The moving information around part is. Huawei claims that in modern computing systems, more than 80% of energy is spent just moving data, not computing with it. The physics behind this is straightforward. Every wire inside a chip resists electrical signals. Every signal has to charge and discharge tiny capacitances. Engineers call this RC delay, and the longer the wire, the worse both effects get. This is a major reason clock speeds in processors have barely increased in about 15 years. So here's the insight. If distance is the problem, what if you could just make the distances shorter? Not by shrinking transistors, but by rearranging where they sit relative to each other. In May 2026, at the IEEE International Symposium on Circuits and Systems in Shanghai, Huawei's semiconductor president, He Tingbo, unveiled what the company calls the Tau scaling law. The name comes from the Greek letter tau, representing the time company, instant in RC circuits. The core argument is straightforward. Instead of continuing the increasingly expensive race to shrink transistors, the industry should optimize directly for minimizing signal propagation time across every level, from individual transistors to entire data centers. The physical implementation is called LogicFolding. Instead of laying out a chip flat, Huawei divides the logic and folds one half on top of the other. Critical paths that used to send signals across several millimeters of silicon now only have to travel a tiny fraction vertically through direct copper bonds between layers. In early results, Huawei reported a transistor density of 238 million transistors per square millimeter, about a 55% gain over their previous flat design at the same manufacturing node. Clock speeds on the upcoming Kirin 2026 chip reportedly reach 3.1 GHz, a 13% improvement. Power efficiency improved by 41%. Here's where we need to be precise. Huawei is not claiming they've invented a 1.4 nanometer manufacturing process. They're saying that by 2031, this architectural stacking approach could achieve transistor density equivalent to what the industry currently labels a 1.4 nanometer process. That distinction matters enormously. Stacking two layers of a mature node does not create a new manufacturing process. It's a system-level trick, not a transistor-level breakthrough. Still, if the performance claims hold, it may not matter. During Huawei's presentation, one specific number caught the attention of semiconductor engineers more than the 1.4 nanometer target: the bonding pitch. 1.5 microns. Here's why this matters. When you stack two chips on top of each other, those layers have to communicate constantly. The connections between them are tiny copper dots that bond directly from one layer to the other. The smaller those dots and the closer together they are, the more connections you can fit, and the faster information can move between layers. The spacing between these connection dots is the bonding pitch. Today, the industry best is around 9 microns. That's what AMD uses in their 3D V-cache memory stacking. TSMC and Intel are in roughly the same range. Huawei is targeting 1.5 microns, 6 times smaller. 6 times more connections per unit of area. To go from 9 microns to 1.5 microns is not a small step. It requires new equipment, new materials, new processes, and new ways of testing whether the bonds actually worked. It's the kind of leap the industry usually takes a decade to achieve, one small step at a time. Huawei's paper describes a key metric called the gear ratio, the ratio between hybrid bonding interconnect pitch and the top metal layer routing pitch. As the ratio approaches 1, two stacked wafers essentially behave like two metal layers on the same die. If Huawei achieves that, the distinction between a chip built on a 7 nanometer process and one built on a leading-edge node starts to blur. Not because the transistors are smaller, because the communication between them is drastically shorter. Now we arrive at the hard part. Stacking logic chips on top of each other creates a heat problem that's genuinely one of the toughest challenges in semiconductor engineering today. Memory chips run cool. They quietly hold data. Logic chips do not. They switch billions of times per second, and every switch generates a tiny bit of heat. Stack two logic layers and you've built a heat sandwich. In a smartphone, there are no fans, no liquid cooling, just a thin slice of metal and maybe a small graphite sheet. Huawei has reportedly integrated chemical vapor deposition diamond layers and micron-level liquid cooling channels into the design to manage thermal concentration. Whether these solutions work at mass production scale is unknown. Then there's yield. A chip that works beautifully in a lab but fails 60% of the time in production is not a product. Huawei claims it has already applied the Tau framework across 381 chip designs over 6 years. That suggests some product. Ion validation exists. But the 1.5 micron bonding target and the thermal density of a smartphone SoC are a different category of challenge. And there's the toolchain. EDA software, the design tools engineers use to lay out chips, must be rewritten to support time-centric optimization across multiple vertical layers. Peking University recently unveiled a prototype EDA tool specifically for LogicFolding, reporting a 30% reduction in total wire length in tests. That's promising, but it's a prototype. The honest answer is that we don't know yet whether this works at commercial scale. The announcement is real. The engineering challenges are real. The outcome is genuinely unknown. Zoom out for a moment. Huawei is not alone in thinking about chips this way. AMD already stacks memory on logic. High bandwidth memory stacks 12 memory dies vertically. Intel and TSMC both have their own 3D packaging roadmaps. TSMC's SoIC platform is already in production for NVIDIA and AMD. Intel's Foveros Direct is entering production. What Huawei is doing is pushing harder and faster toward logic-on-logic stacking, partly by necessity, and partly because they control the entire stack, from mobile devices to cloud infrastructure. Their chief semiconductor scientist, Liao Heng, recently warned that Western chip giants like NVIDIA are approaching insurmountable physical limits in simply building larger chips with more transistors. He framed the AI value chain as an 18-story pagoda, a comprehensive engineering framework where no single layer can be optimized in isolation. What's emerging isn't a single solution. It's a shift in the nature of the race. For most of chip history, competitive position was determined largely at the fab level. Whoever could manufacture the smallest transistors set the performance ceiling. That foundation isn't gone, but it's less determinative. Beyond a certain density threshold, adding more transistors stops delivering proportional gains, because the bottleneck shifts from computation to communication. The semiconductor race may increasingly be about how silicon is arranged and connected, not merely how small individual features become. So where does this leave us? The first real test arrives in autumn 2026, when Huawei's new Kirin smartphone chip goes to market. Industry teardowns will reveal whether the structural novelty is real and whether performance per watt gains hold up. Thermal story is the next signal. If Huawei can manage heat in a fanless smartphone with stacked logic, that suggests serious production readiness. And the broader question is what happens if this works? If 1.5 micron bonding becomes real and manufacturable, other companies will accelerate their own programs. The race won't be over. It will move to a new arena. Huawei's announcement is not proof they've already won. It's proof they're playing. And in a game this important, being a serious player is not nothing. The most honest verdict is this: constraints often redirect innovation rather than stop it. Whether the Dow scaling law becomes an industry framework or a footnote depends on whether it survives the brutal transition from presentation to production. That process will take years, not conference announcements. But the question that matters now is not whether Huawei has secretly built a 1.4 nanometer process. It's whether the entire industry's definition of progress is about to expand.